Hi, this is Nastanyanevsky. We're in a class called Discrete Structures, and we're doing section 1.6 of Rawson Wright's 5th edition of his book, Discrete Mathematics. Okay, this last time let's put everything in context. We talked about sets, then we talked about things in between sets, which are functions. Great. That's what we did in section 1.5. Now we take a short interval, like a musical interval, and we do look at a particular type of function, okay, which will be a sequence. Okay, so functions from the natural numbers to the real numbers are sequences. Okay, and the reason why they're sequences. What's a sequence? It's a list, one of a zeroth thing, a one thing, a second thing, a third thing, of numbers. They're a list of numbers. Okay, so the reason why it's called a sequence is because there's f of 0, and there's f of 1, and there's f of 2, and there's f of 3, and it goes on, etc., etc. Okay, so any function from the natural numbers, they give every single natural number some real number. So we're going to look at a lot of examples of these, and then things we can do with sequences. So let's look at some examples. 1, 2, 3, 4, 5, ... Okay, here's another example. 1, 3, 5, 7, 9, ... So this is all positive numbers. This is all odd numbers. But you can make up other examples like this: 16, 24, 12. It doesn't have to necessarily go up. 93, minus 84.62. Remember, it could be a real number. Okay, 12.85. Okay, 24 could be repeating. I don't care, etc., etc. Okay, here's another one. Sequence 2, 4, 8, 16, 32. 64, ... Okay. Okay. So here's 1, 2, 3, 4 sequences. You might write them as functions. So what is this function? So this is a function that takes a natural number, f of n, and what does it output? Well, it outputs n plus 1. So it doesn't start at 0, it starts at 1. The natural numbers start at 0. Okay. That's a pretty easy thing. How about this? So this is a function that outputs an odd number. So what's an odd number? Well, 2 times n is an even number. 2 times n plus 1 is an odd number. So let's do that. So 2 times n. Well, I don't need that. 2 times n plus 1. Let's plug it in. If you plug in 0, you get 1. That's good. If you plug in 1, you get 3. That's good. If you plug in 2, you get 2 times 2 is 4, plus 1 is 5. So this works. Okay. This is a function from the natural numbers to the natural numbers, but I made up these numbers as I was going along. There's no pattern here whatsoever. So I can't write them as such a function. But it doesn't mean the function doesn't exist. There is a function, I just don't know. I made up those numbers. So here it's easy to calculate with the numbers. Here it's easy to calculate with the numbers. Here you have to go into my head and see what's going on. Anyways, obviously we're not going to talk about such sequences. We're not going to be interested in such sequences, although they are a sequence. Okay, let's do this one. This is f of n is equal to n plus 1. So we're going to start off with 0, 0 plus 1. No. No, it's 2 to the n plus 1. Let's make sure it works. Ready? 0, plug in 0, you're going to get out 2 to the 0 plus 1. 0 plus 1 is 1, 2. Okay, so that's 2 to the 1, so it's 2. And then you plug in 1, you're going to get 1 plus 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16, etc., etc. So this works. Okay? So a lot of times we're going to have sequences, and we can describe the sequences like this. Let's look at some more examples. Okay? The book uses a special notation, and we like the notation. We're going to follow the notation. Okay? It says like this: you should write your sequences as A0, A1, A2, A3, ... Okay? You might want to write it also as B0, B1, B2, B3, ... Okay? So let's look at some examples. Here's a nice example. AN, I'll tell you what AN is. It's equal to 2n. So this is going to correspond to even numbers. 0, 2, 4, 6, 8, ... Okay? Here's another one. B of n, which is equal to 1 over n plus 1. Okay? Okay, now I just have to say, you have to put that n plus 1, the plus 1, because otherwise you're going to have b of 0 is 1 over 0. 1 over 0, we don't divide by 0. Okay, so you need that plus 1. So what does this correspond to? Well, let's plug in 0 here. 0 is going to correspond to 1. 1 over 0 plus 1 is 1. Next, n is equal to 1. 1 over 1 plus 1 is a half. Next, 1 over third. Next, 1 over 4. Next, 1 over 5, ... So that's a sequence of numbers. Okay, let's do number Cn. This is equal to minus 1 to the n. We saw this in the last homework. Okay, so this is going to equal to, what's minus 1 to the 0th power? Anything to the 0th power is a 1. What's minus 1 to the 1 power? Minus 1. What's minus 1 to the 2 power? 1. What's minus 1 to the 3 power? Minus 1. This goes back and forth. Back and forth. 1 minus 1. Odd, even, odd, even. Okay, great. Okay, let's do d of n. d of n is equal to, we had something similar to this in the homework, n over 5. Okay, floor of n over 5. Okay, so let's plug in some values and see what sequence this looks like. Plug in 0 over 5, floor is 0. 1 over 5, floor is 0. 2 over 5, floor is 0. 3 over 5 is 0. 4 over 5 is 0. 5 over 5 is 1. 6 over 5, floor is 1. 7 over 5, floor is 1. 2, 2, 2, 2, 2, 3, 3, ... So basically it's going to repeat the numbers 4 or 5 times. 5 times everything. Okay, let's do another one. E of n is equal to n plus 1 squared. So what do we get? N plus 1 squared. So let's plug in 0. 0 is 1 squared is 1. 1 if this is 1, this is going to be 1 plus 1 is 2. 2 squared is 4. Okay. Next, 3 squared is 9. So these are square numbers. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. ... Okay, so here's 5 nice examples of sequences. Let me just tell you for homework. For homework, you're going to talk about a sequence. A to the n is equal to n minus 1 divided by n plus 1. Okay, great. Now we have to talk about things we can do with a sequence. They don't just exist, we can do something with them. So here's a cute little thing. A0, A1, A2, A3, A4, dot, dot, dot. Okay? What you can do is you can add them up. And the way to do this is like this. I equals 0 till, let's see, do we want to do this forever? We'll do this till K. Okay? A of I. Okay? What this means is, so this is a Greek letter sigma. It's, yes, it means alphabet, but not in this context. Here it means sigma for the word sum. Add them up. Okay? And so this is equal to A of 0 plus A of 1 plus A of 2 plus A of 3 dot 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 plus A of K. Okay? Now you can think of this, you're programmers, you can think of this as a loop. Okay? This is a loop. You start off at here, so this is the variable. You start, this is the start value, this is the ending value. Okay? Okay, so it's a little loop. Okay, great. We're halfway done. Let's show you another thing that you can do. Okay. Take this sequence. Not only can you add up the elements, you can also take the product of the elements. Multiply the elements. Okay, so you do this as follows. You don't have to start at the beginning. You don't have to start at 0. You can start any place you want. So we're going to do this as also. We're going to do I equals 3 till K of AI. Okay, so again, here's your starting value, here's your ending value, and here's your variable that you do it. This is equal to A of 3 times A of 4 times A of 5 times dot 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 times A of K. Okay, multiply them all out. Okay, and again, this also you can do, think of as a loop. Just, I want to show you in terms of a loop, this is what? This is prod equals 1, and then you do for, I don't know if this is Java or C++ or something like that, for I equals 3, of course you can start at 0, okay, semicolon, I less than or equal to K, semicolon, I plus plus, okay, prod equals prod times A sub I. Okay, so that's a nice program that calculates that. Okay, great. Let's do some examples of using this notation, and again, this notation will be used every single day in your classes. They show up all over. They show up outside of math classes too, outside of computer classes too. Okay, so let's use this example. The sum, okay, I'm just going to switch around things here because we don't have to give variables the same name. K equals 0 till 3. Okay, here K is the variable. Whoops. Okay, and so this is K squared plus 1. What is the sum from 0 to 3 of K squared plus 1? This is the sequence that we're doing. So this is going to equal to 0 squared plus 1 plus 1 squared plus 1 plus 2 squared plus 1 plus 3 squared plus 1. That's our boundary. We finish there. So what is this? 0 squared is 0 plus 1 is 1 plus 1 squared is 1 plus 1 is 2 plus 2 squared is 4 plus 1 is 5 plus 3 squared is 9 plus 1 is 10. So 1 plus 2 plus 5 plus 10 is equal to 18. Okay, let's do another one. We'll start over here because we're going to need a little room over here. So this is n is equal to 6, start at 6, end at 10, okay, and do this, 2 to the n minus 3. Made this up, okay. So let's start at 6 minus 3, so we start at 6, 6 minus 3 is 3, 2 to the third is 8. Okay, next. 7 minus 3 is 4, 2 to the 4 is 16, plus 32, so this is 6, 7, 8, plus 64, plus 128. 6, 7, 8, 9, 10. The last one is 10. 10 minus 3 is 7, 2 to the 7 is 128. And if you add this all up, you get 248. Not sure about 246. I'm not sure about that. Oh yeah, no, it works. Okay. Okay, great. Let's do another one. So let's start with another one. We'll do a product, pi I equals 3 till 7 of 2I plus 1. Okay, so this is 2 times 3 plus 1. We start off with 3. Times, we're multiplying, that's P for the product. Pi, that's pi for product. Okay, 2 times 4 plus 1 times 2 times 5 plus 1 times 2 times 6 plus 1 times, we go all the way till 7, 2 times 7 plus 1. Okay, let's see what these numbers are. 2 times 3 is 6 plus 1 is 7 times 8 plus 1, 9 times 11, 2 times 5 is 10, plus 1 is 11, times 13 times 15. Okay, if you multiply all those numbers, you get 1, 3, 5, 1, 3, 5. Okay. Okay, great. Just want to show you something that you've seen before, but I want to put it in this notation. Okay, you've seen factorials. Let's just remind you what it is. N factorial is equal to n times n minus 1 times n minus 2 times n minus 3 times times 3 times 2 times 1. Okay, another way to say that is, we can just write it just another way. 1 times 2 times 3 times 4 times times n minus 3 times n minus 2 times n minus 1 times n. Multiplication goes both ways. A times b is equal to b minus a, so it doesn't matter what order you do it. But another way to write this is, it's the product of I equal 1 till n of I. That's equal to n factorial. Okay? Okay. By the way, that's a very simple sequence, just the numbers. Okay, great. Let me show you where this shows up, and the book talks about it at the end of the section, and it's worth reading it because you're going to see it a lot in data structures and analysis of algorithms. Okay? You have an algorithm, and you're interested in how much work does this algorithm do? How many operations does it do? Well, the answer to that question is usually, okay, it depends on the size of the input. Okay, if you're sorting something, then if you have a small input, it'll take a short amount of time. If you have a large input, it'll take a large amount of time. If you're searching for an element, it depends how many elements you have that you're searching for. If there's a short amount of elements, you have a few. If there's a large, you have a lot. Okay, so what they do in analysis of algorithms, what they do with algorithms is they say, how much work is done? Well, it depends how the size. And basically, you're going to have functions like this. This is usually has a star in it, which tells you how much work is done. So for example, you have some functions that take n squared amount of work to do. Okay, so if you plug in an input of size 1, okay, you're going to get an output of size 1. If you plug an input of size 2, you're going to get an output of size 4. If you plug in an input of size 3, you're going to get 3 squared, you're going to get 9, etc., etc. Okay? Some algorithms work at this speed, some algorithms work at this speed, some algorithms work at this speed, okay? And you characterize, you describe algorithms by these types of functions, okay? These sequences of numbers, okay? So these functions show up as ways of helping you describe how efficient algorithms are, okay? And what you're going to see, I'm just foreshadowing a little for what you're going to see in analysis of algorithms. What you're going to see is you're going to see lots of different algorithms. Some of them are n squared, some of them are n, some of them are n to the third, okay? Some of them are n to the fourth, okay? This is how much growth it takes. Some of them are 2 to the n. 2 to the n means it does a lot of work, exponential amount of work. So such algorithms are not very efficient. For inputs, they take trillions of years to solve. Also, n factorial, that's even worse. Also, here's something that's even worse. But you could always find a worse algorithm. Now, some things like square root of n is over here. N log n is over there. Okay? And you also have, so square root of n is n to the half. You also have log of n. There's some algorithms, like the binary search, which take only log of n. Okay? And so you have this sequence of sequences, actually. You have this list of sequences. In analysis of algorithms and data structures, you decide where your algorithm is, how much work it does. Okay? Anyways, so let's just recap what we did today. This was like a short musical interval. We talked about functions, and now we wanted to talk about a specific type of functions from the natural numbers to the real numbers. We called them sequences. We did a lot of examples of them. We showed what you can do with the sequence, and we also related it to something that we'll see in analysis of algorithms. For those of you interested, you can watch my video. It's in chapter 3 of the analysis of algorithms. Very important chapter. It'll help you for the rest of your computer science career. Have a wonderful day.